It's always fun introducing people who need no introduction. But for those of you who don't know Jeff and his work, he pretty much created, he helped create the field of machine learning as it now exists, and was on the cutting edge back when it was the bleeding edge of statistical machine learning and neural nets when they first made their resurgence for the first time in our lifetime, and has been a constant force pushing it, pushing the analysis and the field away from just sort of the touchy-feely, let's tweak something till it thinks, and towards building systems that we can understand and that actually do useful things that make our lives better. So if you read the talk announcement, you've seen all of his many accomplishments and members of various royal societies, et cetera, so I won't list those. I think instead of taking up more of his time, I'm just going to hand the microphone over to Jeff.
Thank you. I've got one here. So the main aim of neural network research is to make computers recognize patterns better by emulating the way the brain does it. We know the brain learns to extract many layers of features from the sensory data. We don't know how it does it, so it's a sort of joint enterprise of science and engineering. The first generation of neural networks, I can give you a 2-minute history of neural networks. The first generation were things like perceptrons, where you had hand-coded features. They didn't adapt, so you might put an image, the pixels of an image here, have some hand-coded features, and you'd learn the weights to decision units, and if you wanted funding, you'd make decision units like that. These were fundamentally limited in what they could do, as was pointed out in 1969, and so people stopped doing them. Then, sometime later, people figured out how to change the weights of the feature detectors as well as the weights of the decision units. So what you would do is take an image here, you go forwards through a feed-forward neural network, you would compare the answer the network gave with the correct answer, you take some measure of that discrepancy, and you send it backwards through the net, and as you go backwards through the net, you compute the derivatives for all of the connection strengths here, both those ones and those ones and those ones, of the discrepancy between the correct answer and what you got, and you change all these weights to get closer to the correct answer. That's backpropagation, and it's just the chain rule. It works for nonlinear units, so potentially these can learn very powerful things, and it was a huge disappointment. I can say that now because I got something better. Basically, we thought when we got this that we can now learn anything, and we'll get lots of layers of features, object recognition, speech recognition, it'll all be easy. There's some problems. It worked for some things. Jan LeCun can make it work for more or less anything. But in the hands of other people, it has its limitations. And something else came along. So there was a temporary digression called kernel methods, where what you do is you do perceptrons in a cleverer way. You take each training example, and you turn a training example into a feature. Basically, the feature is how similar are you to this training example. And then you have a clever optimization algorithm that decides to throw away some of those features and also decides how to weight the ones it keeps. But when you're finished, you've just got these fixed features produced according to a fixed recipe that didn't learn, and some weights on these features to make your decision. So it's just a perceptron. There's a lot of clever math to how you optimize it, but it's just a perceptron. And what happened was people forgot all of Minsky and Pappert's criticisms about perceptrons not being able to do much. Also, it worked better than backpropagation at quite a few things, which was deeply embarrassing, but it says a lot more about how bad backpropagation was than about how good support vector machines are. So if you ask what's wrong with backpropagation, it requires labeled data. And some of you here may know it's easier to get data than labels. If you have it as a model of the brain, you've got about that many parameters, and you live for about that many seconds, actually twice as many, which is important to some of us. There's not enough information in labels to constrain that many parameters. You need 10 to the 5 bits or bytes per second. There's only one place you're going to get that, and that's the sensory input. So the brain must be building a model of the sensory input, not of these labels. The labels don't have enough information. Also, the learning time didn't scale well. You couldn't learn lots of layers. The whole point of backpropagation was to learn lots of layers, and if you gave it like 10 layers to learn, it would just take forever. And then there's some neural things I won't talk about. So if we want to overcome these limitations, We want to keep the efficiency of a gradient method for updating the parameters, but instead of trying to learn the probability of a label given an image, where you need the labels, we're just going to try and learn the probability of an image. That is, we're going to try and build a generative model that if you ran it will produce stuff that looks like the sensory data. In other words, we're going to try and learn to do computer graphics. And once we can do that, then computer vision is just going to be inferring how the computer graphics produce this image. So what kind of a model could the brain be using for that? The building blocks I'm going to use are a bit like neurons. They're intended to be a bit like neurons. They're these binary stochastic neurons that get some input. They give an output that's either a 1 or a 0, so it's easy to communicate, and it's probabilistic. So this is the probability of giving a 1 as a function of the total input you get, which is your external input plus what you get from other neurons, times the weights on the connections. And we're going to hook those up into a little module that I'll call a restricted Boltzmann machine. This little module here has a layer of pixels and a layer of feature detectors. So it looks like it's never going to learn lots and lots of layers of feature detectors. It looks like we've thrown out the baby with the bathwater, and we're now just restricted to learning one layer of features, but we'll fix that later. We're going to have a very restricted connectivity, hence the name, where this is going to be a bipartite graph. The visible units, for now, don't connect to each other, and the hidden units don't connect to each other. The advantage of that is, if I tell you the state of the pixels, these become independent, and so you can update them independently and in parallel. So given some pixels, and given that you know the weights on the connections, you can update all these units in parallel. And so you've got your feature activations very simply. There's no lateral interactions there. These networks are governed by an energy function, and the energy function determines the probability of the network adopting particular states, just like in a physical system. These stochastic units will kind of rattle around, and they'll tend to enter low energy states and avoid high energy states. The weights determine the energies linearly. The probabilities are an exponential function of the energies. So the probabilities, the log probabilities are a linear function of the weights, and that makes learning easy. There's a very simple algorithm that Terry Sinofsky and me invented in about 1982. In a general network, you can run it, but it's very, very slow. In this restricted Boltzmann machine, it's much more efficient. And I'm just going to show you what the maximum likelihood learning algorithm looks like. That is, suppose you said, take one of your parameters on your connection. How do I change that parameter so that when I run this machine in generative mode, in computer graphics mode, it's more likely to generate stuff like the stuff I've observed? And so here's what you should do. You should take a data vector, an image, and you should put it here on the visible units. And then you should let the visible units, via their current weights, activate the feature detectors. So you provide input to each feature detector, and you now make a stochastic decision about whether the feature detector should turn on. Lots of positive input, it almost certainly turns on. Lots of negative input, it almost certainly turns off. Then, given the binary state of the feature detectors, we now reconstruct the pixels from the feature detectors. And we just keep going like that. And if we run this chain for a long time, this is called a Markov chain, and this process is called alternating Gibbs sampling. If we go backwards and forwards for a long time, we'll get fantasies from the model. This is the kind of stuff the model would like to produce. These are the things that the model shows you when it's in its low energy states, given its current parameters. So that's the sort of stuff it believes in. This is the data. And obviously you want to say to it, believe in the data, not your own fantasies. And so we'd like to change the parameters, the weights on the connections, so as to make this more likely and that less likely. And the way to do that is to say, measure how often a pixel I and a feature detector J are on together when I'm showing it the data vector V, and then measure how often they're on together when the model is just fantasizing, and raise the weights by how often they're on together when it's seeing data, and lower the weights by how often they're on together when it's fantasizing. And what that'll do is it'll make it happier with the data, lower energy, and less happy with its fantasies. And so its fantasies will gradually move towards the data. If its fantasies are just like the data, then these correlations, the probability of pixel I and feature detector J being on together in the fantasies, will be just the same as in the data, and so it'll stop learning. So it's a very simple local learning rule that a neuron could implement, because it just involves knowing the activity of a neuron and the other neuron it connects to. And that will do maximum likelihood learning, but it's slow. You have to settle for like 100 steps. So I figured out how to make this algorithm go 100,000 times faster. The way you do it is instead of running for 100 steps, you just run for 1 step. So now you go up, you come down, and you go up again. And you take this difference in statistics, and that's quite efficient to do. It took me 17 years to figure this out, and in that time, computers got 1,000 times faster. So the change in the weight now is the difference is a learning rate times the difference between statistics measured with the data and statistics measured with reconstructions of the data. That's not doing maximum likelihood learning, but it works well anyway. So I'm going to show you a little example. We're going to take a little image where we're going to have handwritten digits. This is just a toy example. We're going to put random weights on the connections. Then we're going to activate the binary feature detectors, given the input they're getting from the pixels. Then we're going to reconstruct the image. And initially, we get a lousy reconstruction. This will be very different from the data because they're random weights. And then we're going to activate the feature detectors again. And we're going to increment the connections on the data. And we're going to decrement the connections on the reconstructions. And that is now going to learn nice weights for us, as I'll show you, nice connection strengths that will make this be a very good model of handwritten twos. It's important to run the algorithm where you take the data, and on the data you increment connection strengths. And on your this is really a sort of screwed up version of the data that's been infected by the prejudices of the model. So the model kind of interprets the data in terms of its features. Then it reconstructs something it would rather see than the data. Now, you could try running a learning algorithm where you take the data, you interpret it, you imagine the data is what you would like to see, and then you learn on that. That's the algorithm George Bush runs, and it doesn't work very well. So after you've been doing some learning on this for not very long, I'm now showing you 25,000 connection strengths. Each of these is one of the features. Take this guy. That's a feature. And the intensity here shows you the strength of the connection to the pixels. So this feature really wants to have these pixels off, and it really wants to have these pixels on, and it doesn't care much about the other ones. Mid-gray means 0. And you can see the features are fairly local. And these features are now very good at reconstructing twos. It was trained on twos. So if I show it some twos it never saw before and get it to reconstruct them, you can see it reconstructs them pretty well. The funny pixels here, which aren't quite right, is because I'm using Vista. So you can see the reconstruction is very like the data. And it's not quite identical, but it's a very good reconstruction for a wide variety of twos, and these are ones it didn't see during training. OK. Now what I'm going to do, that's not that surprising. If you just copied the pixels and copied them back, you'd get the same thing, right? So that would work very well. But now I'm going to show it something it didn't train on. And what you have to imagine is that Iraq is made of 3s, but George Bush thinks it's made of 2s. OK, so here's the real data, and this is what George Bush sees. That's actually inconsistent with my previous joke, because it assumes he runs this learning algorithm. Sorry about that. OK, so you see that it perverts the data into what it would like to believe, which is like what it's trained on. OK, that was just a toy example. Now what we're going to do is train a layer of features like that in the way I just showed you. We'll get these features that are good at reconstructing the data, at least for the kind of data it's trained on. And then we're going to take the activations of those features, and we're going to make those data and train another layer. OK? And then we're going to keep doing that. And for reasons that are slightly complicated, and I will partially explain, this works extremely well. You get more and more abstract features as you go up. And once you've gone up through about 3 layers, you've got very nice abstract features that are very good then for doing things like classification. But all these features were learned without ever knowing the labels. It can be proved that every time we add another layer, we get a better model of the training data. Or to be more precise, we improve a lower bound on how good a model we got of the training data. So here's a quick explanation of what's going on. When we learn the weights in this little restricted Boltzmann machine, those weights define the probability of, given a vector here, reconstructing a particular vector there. So that's the probability of a visible vector given a hidden vector. They also define this whole Markov chain if you went backwards and forwards many times. So if you went backwards and forwards many times and then look to see what you get here, you'll get some probability distribution over hidden vectors, and the weights are defining that. And so you can think of the weights as defining both a mapping from these vectors of activity over the hidden units to the pixels, to images, that's this term, and the same weights define a prior over these patterns of hidden activities. When you learn the next level Boltzmann machine up, you're going to say, let's keep this mapping, and let's learn a better model of the posterior that we got here when we used this mapping. And you keep replacing the implicit posterior defined by these weights by a better one, which is the P of V given H defined by the next Boltzmann machine. And so what you're really doing is dividing this task into two tasks. One is, find me a distribution that's a little bit simpler than the data distribution. Don't go the whole way to try and find a full model. Just find me something a bit simpler than the data distribution that's going to be easier for a Boltzmann machine to model. That's very non-parametric. And then find me a parametric mapping from that slightly simpler distribution to the data distribution. So I call this creeping parameterization. What you're really doing is it's like taking the shell off an onion. You've got this distribution you want to model. Let's take off one shell, which is this, and get a very similar distribution that's a bit easier to model, and some parameters that tell us how to turn this one to this one, and then let's go and solve the problem of modeling this distribution. So that's what's going on when you learn these multiple layers. After you've learned, say, 3 layers, you have a model that's a bit surprising. This is the last restricted Boltzmann machine we learned. So here we have this sort of model that says, to generate from the model, go backwards and forwards. But because we just kept the P of V given H for the previous models, this is the directed model where you sort of go chunk, chunk to generate. So the right way to generate from this combined model, when you've learned 3 layers of features, is to take the top 2 layers and go backwards and forwards for a long time. It's fortunate you don't actually need to generate from it. I'm just telling you how you would if you did. We want this for perception. So really, you just need to do perceptual inference, which is chunk, chunk, chunk. It's very fast. But to generate, you'd have to go backwards and forwards for a long time. And then once you've decided on a pattern here, you just go chunk, chunk. That's very directed and easy. So I'm now going to learn a particular model of some handwritten digits, but all the digit classes now. So we're going to put slightly bigger images of handwritten digits from a very standard data set where we know how well other methods do. In fact, it's a data set on which support vector machines beat backpropagation, which was bad news for backpropagation, but we're going to reverse that in a minute. We're going to learn 500 features now instead of 50. Once we've learned those, we're going to take the data, map it through these weights, which are just these weights in the opposite direction, and get some feature vectors. We're going to treat those as data and learn this guy. Then we're going to take these feature vectors. We're going to tack on 10 label units. So now we needed the labels, but I'll get rid of that later. And so we get a 510-dimensional vector here. And we're going to learn a joint density model of the labels and the features. We're not trying to get from the features to the labels. We're trying to say, why do these two things go together? So we're learning a joint model of both, not a discriminative model. When we've completed this learning, what we're going to end up with is the top level here is a Boltzmann machine, and so it has an energy function. And you can think of that as a landscape. When the weights are all small here, or close to 0, then the energy landscape is very flat. All the different configurations here are more or less equally good. As it learns, it's going to carve ravines in this energy landscape. If you think of it as a 510-dimensional energy landscape, these ravines are going to have the property that in the floor of the ravine, there's about 10 degrees of freedom. And those are the ways in which a digit can vary and still be a good instance of that digit, like a 2 with a bigger loop or a longer tail. Up the sides of the ravine, there's like 490 directions. And those are the ways in which if you varied the image, it wouldn't be such a good 2 anymore. But the nice thing is, it's going to learn long, narrow ravines so that one 2 can be very different from another 2, and yet connected by this ravine. The ravine's captured the manifold. So it could wander from one to another in a way that it won't wander from a 2 to a 3, even though the 3 might be more similar in pixels to the 2. Okay. I want to show you this generative model actually generating. Before I do that, I want to own up. We did a little bit of fine-tuning, which actually took longer than the original learning, where you, after you've done that greedy layer-by-layer learning, you do a bit of fine-tuning where you put in images, you do a forward pass, bottom up, with binary states. And when you do this forward pass, you adjust the connection slightly so that what you get in one layer will be better at reconstructing what caused it in the layer below. Then you do a few iterations at the top level Boltzmann machine. You go backwards and forwards a few times to get the learning signal there. And then you do a down pass. And during the down pass, you adjust the connections going upwards so that they're better at reconstructing what caused the activity in that layer. So during the down pass, you know what caused activity because you caused it, and you try and recover those causes. That fine-tuning helps, but it'll work without it. So now I'm going to attempt to show you a movie. That's not very nice. OK, there's that network. Here's where we're going to put images. Here's 500 features, 2,000 features, and the 10 labels. First of all, we'll get it to do some perception. So I'm going to give it an image and tell it to run forwards. Oops, sorry, I didn't mean that. I meant that. And you'll see these are stochastic. They keep changing. But it's very sure that it's a 4. See, those are the identities of these neurons. It knows that's a 4, and it has no doubt about it, even though its feature detectors are fluctuating a bit. If I give it a 5, hopefully it'll think it's a 5. Yeah, it doesn't have any doubt. So now let's be mean to it, because that's a lot more fun. I'm going to give it that. So it says sort of 4, 6, 8, 4, 8, 8, 8, 8, 8, 8, 4. It can't make up its mind whether it's a 4 or an 8. And that's pretty reasonable in those circumstances. It will actually, for that one, say 8 a bit more often than anything else. So we class it as getting that right. But it's very unsure whether it's an 8 or a 4. And just occasionally it thinks it can be other things like a 2. But it basically thinks 4 or 8. I can make it run faster so you can... It's basically 4 or 8 and an occasional 6. I could give it something like this. And it thinks basically 1 or 7 and occasionally a 4. Because I programmed this myself, I want to point out that it's very reasonable for this. This is my baby. And it's very reasonable for it to think that might be a 4, because look, you can see the 4 in there. OK. OK. Now, that was just doing perception, but the very same model does generation. So what I can do is I can fix a top-level unit. And all I've done is I've fixed the state of one neuron. There's a million connections there, because that's 2,000 to 500. I just fixed this one neuron. But when I fix that state, then the weights, the 2,000 weights coming out of there to these neurons here, what they'll do is they'll lower the energy of the ravine for 2s, and they'll raise the energy of the ravine for all the other guys. So now we've got this landscape in which we've got all these ravines, but the 2 ravine has been lowered. And if we put it at a random point, it will eventually stumble into the 2 ravine, and then it'll stay there and wander around. So let's see if we can do that. So what's really going on here is I'm just going backwards and forwards up here. Ignore that for now. I'm going backwards and forwards here and letting it gradually settle until it's into a state that this network's happy with. So that's its brain state, and that doesn't mean much to you. If you look at that, you don't really know what it means. So what we're going to do is, as it's settling, we're going to play out the generative model here. We're going to do computer graphics to see what that would have generated. And so what you've got here is that's what's going on in its brain, and this is what's going on in its mind. So you can see what this is thinking. And I'm serious about that. That is, I know it sounds crazy. When I say to you, I'm seeing a pink elephant, what I mean is, I've got a brain state such that if there were a pink elephant out there, this would be perception. That's how mental states work. They're funny because they're hypothetical, not because I made a spooky stuff. So I use this language where the terms refer to things in the world because I'm saying what would have to be in the world for this brain state to be perception. Now, if I've got a generative model, I can take the brain state and say, well, what would have to be in the world for that to be perception? Well, that. So that's what it's thinking. That's its mental state right there. So you've got brain states and mental states. And most psychologists won't show you both. Let's go a bit faster. And it still hasn't settled into the 2 ravine, and now it's about in the 2 ravine. And now it's just wandering around in that 2 ravine, and this is what it's thinking. It knows about all sorts of different 2s, and it's very good that it does, because that means it can recognize weird 2s. Let's give it another one. It hasn't got into the 8 ravine properly yet. It'll jump out into other ravines because it's not really there. But by about now, it'll be in the 8 ravine. And it'll show you all the sorts of different 8s it believes in if you run it long enough. If you ran it for an hour now, it would probably just stay in the 8 ravine showing you all sorts of different 8s. OK. Let's do one more because I like it so much. Again, it's not really in the 5 ravine properly yet. Look, there was a 6. By about now, it's in the 5 ravine. And it'll show you all sorts of weird 5s, ones without tops and occasional 6s. And it ends up with a pretty weird one. But that's definitely a 5. And it's very good that it knows that that's definitely a 5, because it allows it to recognize things like that. OK, that's it for the demo. How do I get rid of that? OK, so here's some examples of things it can recognize. These are all ones it got right. And you can see it recognizes a wide variety of 2s. It recognizes that this is a 1 despite that. And it recognizes that this is a 7 because of that. If you try writing a program by hand that'll do that, you'll find it's kind of tricky if you'd never thought of these examples in advance. If you compare it with support vector machines, now what we're doing here is we're taking a pure machine learning task. We're not giving it any prior knowledge about pixels being next to other pixels. We're not giving it extra transformations of the data. So this is it's a pure machine learning task without any extra help. If you give extra help, you can make all the methods a lot better. But a support vector machine done by DeCoste and Scholkopf, who are very good, got 1.4%. The best you can do with standard backpropagation is about 1.6%. This gets 1.25%, and significance here is about a difference of 0.1. So this is significantly better than that. K nearest neighbor gets 3.3%. Now, I fine-tuned that to be good at generation, so I could show you it generating, using this sort of up-down algorithm. But we can also use backpropagation for fine-tuning. And now that I've got this way of finding features from the sensory data, I can say things like, nobody in their right mind would ever suggest that you would use a local search technique like backpropagation to search some huge nonlinear space by starting with small random weights. It'll get stuck in local optima. And that is indeed true. What we're going to do is we're going to search this huge nonlinear space of possible features by finding features in the sensory data, and then finding features in the combinations of features we found in the sensory data, and keep doing that. And we'll design our features like that. So we didn't need labels. We just needed sensory data. Once we've designed all our features, we can then use backpropagation to slightly fine-tune them to make the category boundaries be in the right place. So a pure version of that would be to say, let's learn the same net, but without any labels. OK, so we do all the pre-training like this. After we've pre-trained now, what we're going to do is we're going to attach 10 label units to the top, and we're going to use backpropagation to fine-tune these. And the fine-tuning is hardly going to change the weights at all, but it's going to make the discrimination performance a lot better. So this is going to be discriminative fine-tuning, and that gets 1.15% errors. And all the code for doing the pre-training and the fine-tuning is on my webpage if you want to try it. Now, given that we now know how to get features from data, we can now train things we never used to be able to train with backpropagation. If you take a net like this, where we're going to put in a digit, and we're going to try and get out the same digit, but we're going to put like 8 layers of nonlinearities in between, if you start with small random weights and you backpropagate, you get small, small times small, and by the time you get back here, you get small to the power of 8, and you don't get any gradient. If you put in big random weights, you'll get a gradient, but you'll have decided in advance where you're going to be in the search space. what we're going to do is learn this Boltzmann machine here. After we've learned that, we're going to map the data to get activity patterns, then learn this Boltzmann machine. Then we're going to learn this Boltzmann machine. Then we're going to learn this Boltzmann machine, but with linear hidden units. And then what we're going to do is put the transposed weights here, because this is good at reconstructing that. So this should be good at, and so on. And we're going to use that as a starting point. And then we do backpropagation from there, and it'll slightly change all of these weights, and it'll make this work really well. And so now what it's done is it's communicated this 28 by 28 image via this bottleneck of 30 units, but using a highly nonlinear transformation to compress it. If you make everything linear here, you leave out all these layers and make everything linear, this is PCA, principal components, which is a standard way to compress things. If you put in all these nonlinear layers, it's much better than PCA. So this is all done without labels now. You just give it the digits. You don't tell it which is which. These are examples of the real digits, just one example of each class. These are the reconstructions from those 30 activities in the hidden layer. And you can see they're actually better than the data. This is a dangerous line of thought. PCA does this, and you can see it's kind of hopeless compared with this method. At least that's what you're meant to see. Now, we could apply this to document vectors. I don't find documents as interesting as digits, but I know some people are interested in them. You could take a document vector, and you could take the counts of the 2,000 most common words, and there's a big database like this of 800,000 documents. And so we took 400,000. Sorry, yeah, I know, I see people smiling. Big 800,000, I'm an academic, okay? We then train up a neural net like this, where these are now Poisson units. For those of you who know machine learning, we can use any units in the exponential family, where the log probability is linear in the parameters. So we train up this to get some features, we train up this to get some features, and then we train up this to get just 2 linear features. That seems a little excessive, and obviously when we reconstruct, we're not going to get quite the right counts. But you'll get counts that are much closer to the right counts than the base rates. So if down here you have a high count for Iraq and Cheney and torture, up here you'll get high counts for similar things. So we can turn a document into a point in a 2-dimensional space. And of course, once we've got a point in a 2-dimensional space, we can plot it in 2D. And for this database, someone had gone through by hand, more or less by hand, and labeled all the documents. We didn't use the labels, okay? But now when we plot the point in 2D, we can color the point by the class of the document. So if you do the standard technique, which is latent semantic analysis, which is just a version of PCA, and you lay out these documents in 2D, that's what you get. And you can see the green ones are in a slightly different place from these blue ones, but it's a bit of a mess. If you use our method, it does a little bit better. You get that. And so now, if you look at these are business documents, right? If you look at these documents here, you can see there's lots of different kinds of documents about accounts and earnings. Presumably there's an Enron cluster in here somewhere. And it would be very nice to know which other companies are in this Enron cluster. Okay. But there's something more interesting you can do. That's just for visualization. But now I'm going to show you how to solve the following problem. Suppose I give you a document. So this isn't like what I call Google search, where you use a few keywords and you find what you want. This is I give you a document, and I ask you to find similar documents to the one I gave you. Okay, documents with similar semantic content. So I'm using a document as a query. What we're going to do is we're going to take our big database of documents, a whole million of them, and we're going to train up this network, and it's going to convert these documents into 30 numbers. I'm going to use logistic units here, that is numbers that range between 1 and 0. And we're going to train it as Boltzmann machines. Then we're going to backpropagate, and we'll get intermediate values here that convey lots of information. And then we're going to start adding noise here. And we're going to add lots and lots of noise. Now, if I add lots and lots of noise to something that has an output between 0 and 1, there's only one way it can transmit a lot of information. It's got to make the total input that comes from below be either very big and positive in which case it'll give a 1, or very big and negative, in which case it'll give a 0. And in both those cases, it will resist the noise. If it uses any intermediate value, the outcome will be determined by the noise, so it won't transmit information, so it won't be very good at getting the right answers.
So the noise is something like Gaussian. It's not binary flipping.
It's Gaussian noise. And we gradually increase the standard deviation, and it's noise in the input to the unit. And we gradually increase this, and we use a funny kind of noise that I don't want to get into that makes it easier to use conjugate gradient descent. And what will happen is these will turn into binary units. So we now have a way of converting the word count vector of a document into a 30-bit binary vector. And now we can do what I call supermarket search. So suppose you want to find things that are like a can of sardines. What you do is you go to your local supermarket, and you say to the cashier, where do you keep the sardines? And you go to where the sardines are, and then you just look around. And there's all the things similar to sardines, because the supermarket arranged things sensibly. Now, it doesn't quite work, because you don't find the anchovies, as I discovered when I came to North America. I couldn't find the anchovies. They weren't anywhere near the sardines and the tuna. That's because they're near the pizza toppings. But that's just because it's a 3-dimensional supermarket. If it was a 30-dimensional supermarket, they could be close to the pizza toppings and close to the sardines. So what we're going to do is we're going to take a document, and using our learned network, we're going to hash it to this 30-bit code. But this is a hash code that was learned. It's not some random little thing. It was learned with lots of machine learning, so it has the property that similar documents map to similar codes. So now we can use hashing for doing approximate matches. Everybody knows hashing is nice and fast, and everybody knows it can't do approximate matches. But with machine learning, you can have both. So we take our document, we hash it to a code, and in this memory space, at each point in the memory space, we put a pointer to the document that has that code. And you're engineers, so if 2 documents have the same code, you can figure out what to do. So now, with the query document, we just go there, and now we just look around, like in the supermarket. And the nearby similar documents will have nearby codes. And so all you need to do to find a similar document is flip a bit and do a memory access. Okay, that's 2 machine instructions. So if you were to have a database of, say, 10 billion documents, and I give you one and say, give me 100,000 documents similar to this one for my other search technique I'm going to use that can only cope with 100,000, you're going to have to do 100,000 times. You're going to have to flip a bit and do a memory access. So that's only 200,000 machine instructions. Only 2 machine instructions per document. It's completely independent of the size of your database. Okay, because you've laid things out like in a supermarket. You've got a document supermarket now in 30D. So if you compare it with, well, we've actually only tried it because we're academics on 20-bit codes and 1 million documents, and it works just fine. But nothing could possibly go wrong when you scale it up. It's actually quite accurate. That is, if you compare it with a sort of gold standard method, it's about the same accuracy. And when you now take your shortlist that you found in this very fast way, and you give those guys in the shortlist to the gold standard method, it works better than the gold standard method alone. It's much better than locality-sensitive hashing, both in terms of speed. We use the code that's on the web for that, and it's about 50 times faster. And in terms of accuracy. Locality-sensitive hashing will always be less good than this because it's just a hack for doing this. And locality-sensitive hashing works on the count vector. And if you work on the count vector, you will never understand the similarity between the document that says Gonzalez quits and the document that says Wolfowitz resigns. They're very similar, but not in the word count vector. But if you've compressed it down to some semantic features, they're very similar documents. So the summary is that I showed you how to use this simple little Boltzmann machine with the bipartite connections to learn a layer of features. Then I showed you that if you take those features, you can learn more features. And as you go up this hierarchy, you get more and more complicated features that are going to be better and better for doing classification. This produces good generative models that are good at reconstructing data, at producing data like the data you saw, if you fine-tune with this sort of up-down algorithm, which has this funny name. If you want good discriminative models, what you do is then you fine-tune with backpropagation. But the good news is you don't need labels for all your training data. You can learn all these features on a very big data set, and then with just a few million labels, or even a few hundred labels, you can backpropagate to fine-tune it for discrimination. And that'll work much better than, for example, using any machine learning method that just uses the labeled data. It's a huge win. You can use the unlabeled data very effectively. And I've shown you that it can also be used for explicit dimensionality reduction, where you go down to a bottleneck, and that you can do search for similar things very fast. And of course, we'd like to apply it to images, but for images you have a problem, which is in documents, a word is very indicative of what the document's about. In an image, what's indicative of what the image is about is a recognized object. And so what we're trying to do now is make it recognize objects so that then we can get the objects in the image and then apply this semantic hashing technique. But we haven't done that yet. I see I've managed to talk very fast, so I can show you a little bit about how we're going to do the image recognition. Suppose you want to do a generative model which would allow you, a graphics model, to take a type of an object and produce an image of that object. So I say square, and I say what its pose is, its position and orientation. Then we might have a top-down model that from this and this predicts where the parts might be. And if it's a kind of sloppy model, it'll say this edge ought to be round about there, and this edge ought to be round about there. And if we pick randomly from these distributions, we'll get a square where the edges don't meet up. Now, one way we could solve that is to generate very accurately here. We could say, I'm going to generate each piece just right. But that requires high bandwidth and lots of work. We're going to generate sloppily. We're going to generate a redundant set of pieces. And then we're going to know how the pieces fit together. We're going to know a corner must be collinear with an edge. And the edges here must be collinear with corners. And now by lateral interactions here, using something called a Markov random field, we can get it to settle down to that. And so now our generative process is, at each level, the level above says where the major pieces should be, roughly, and a level that knows about how these pieces go together, like how eyes and noses and mouths go together, says, OK, the nose should be exactly above the middle of the mouth, and the eyes should be at exactly the same height. The level above doesn't need to specify that. That's known locally. So how are we going to learn that? Well, we're going to introduce lateral interactions between the visible units. That's fine. The real crucial thing in these nets is you don't have lateral interactions between the hidden units. So we can learn that. And the way we learn that is we put an image in here. We activate the features. Then with the features fixed, providing constant top-down input, we run these lateral interactions to let this network settle down. And we replace the binary variables by real value variables, so we're doing something called mean field. We let it settle down to something it's happier with, a reconstruction. It doesn't need to get all the way to equilibrium. It just needs to get a bit better than this. And then we apply our normal learning algorithm to these correlations and these correlations, like this. But we can also learn the lateral interactions by saying take the correlations in the data minus the correlations in the reconstructions, and that'll learn all these lateral interactions. So now what we're going to do is we're going to learn a network with 400 input units for a 20 by 20 patch of an image. This is just preliminary work. When we learn the first network, these aren't connected. Then when we use these feature activities to learn the second level Boltzmann machine, we connect these together, and we learn these and these. Then when we learn the top Boltzmann machine, we connect these together, and we learn these weights and these weights. When we're finished, we can generate from the model. And so as a control, what we're going to do is we're going to learn this model on patches of natural images, which are notoriously hard things to model, because anything could happen in a patch of natural image. So it's a very hard thing to build a density model of. We're going to learn it without lateral connections, and we get a model that's very like many other models. When you generate from it, what you get is clouds. So here's natural image patches. And they have the property that there's not much going on, and then there's a sudden outbreak of structure, like here. So if you apply a linear filter to these things, the linear filter will usually produce a 0 and occasionally produce a huge output. If you apply a linear filter to these things, it'll produce some kind of Gaussian distribution. These have exactly the same Fourier spectrum as these. What they don't have is this sort of heavy-tailed distribution where there's not much happening and then a lot happening. And long-range structure. So now what happens if we put in the lateral interactions and do the learning again If we put the lateral interactions in, they can say things like, if you have a piece of edge here, and you'd like a piece of edge somewhere around here, put it here where it lines up. So that'll make much longer range interactions. And so now when we generate from the model with lateral interactions, we get that. And you can see that these are much more like real image patches. They pass many of the statistical tests for being real image patches. They've got this kind of much longer range structure. They've got sort of collinear things and things at right angles and all sorts of nice structure in them, which we didn't have before. And so we're getting, this is probably the best model there is of natural image patches. If you ask anybody else who models them, show me samples from your generative model, they say, oh, well, we tried that and they look terrible, so we never publish those. This is, I think, the first model that generates nice samples from the model. Zhu has a model that's maybe comparable. What we'd like to do now is make more layers, and we'd also like to have attention so that as you go up, you focus on parts of the image. And what I want to do is get something, you give it an image, you go up, it's focusing on parts, and it gives you a figure at the top. It gives you what you see, which is you look at an image and you see a face. And then you look again and you see the eye. Then you look again and you see a group of 4 people. And those are the things that come out, and those are going to be like the words that need to go into an image retrieval system. You're going to have, this is going to run for a long time learning, and then it's going to run for quite a long time on each image, but that's all offline. OK, I'm done.
It looks like we've got time for questions. If you have questions, can you please hit the mic in the middle so that the folks out of their offices can hear?
Okay. Hi. You were saying that this method doesn't require labels. I was just wondering if it would actually help if you have labels for at least some of your training data.
Oh, yes. Labels help. The main thing is to show that you can do a lot without them, and therefore you can get much more leverage from a few labels. Yeah.
Okay, thanks.
So, for example, in the semantic hashing idea, you could, as you're learning those 30-dimensional codes, you could say if 2 things are from the same class and the codes are far apart, introduce a small force pulling them together. And we've got a paper on that in AI Stats last year. And that will improve the sort of clustering of things of the same class. But the point is you can do it without knowing the classes as well.
Hi. So people have built autoencoders for a long time before, and they use regular sigmoid units and use backprop to train them.
But they never worked very well.
Correct. If we actually had multiple layers of these sigmoid units and train them in the same fashion as you're doing, 1 layer at a time, would it work as well as RBMs or not? OK, that's a very good question. So it's a bit confusing. This deep thing with multiple layers trained with RBMs I called a multi-layer autoencoder. But you could also have a very small autoencoder with 1 hidden layer that's nonlinear and train that up. And the RBM is just like that. So you could train these little autoencoders and stack them together and then train the whole thing with backprop. That's what the question was. And that will work much better than the old way of training autoencoders, but not quite as well as this. So Yoshua Bengio has a paper where he compared doing autoencoders with doing restricted Boltzmann machines. And the restricted Boltzmann machines work better, especially for things like cluttered backgrounds.
I've got a question, which I get to ask because I'm holding a microphone. So this morning, we were talking about about news, where the problem with news is that everything changes from day to day. Do you have any intuition, and this is one of those unfair, what do you think would happen? Do you have any intuition on how hard it would be to adapt a deep network like this once your input distribution changes or as it continues to change? OK,
so one good thing about this learning is everything scales linearly with the amount of training data. There's no quadratic optimization anywhere that's going to screw you for big databases. The other thing is, because it's basically stochastic online learning, if your distribution changes slightly, you can track that very easily. You don't have to start again. So if it's the case that the news tomorrow has quite a lot in common with the news over the last few months and few years, and you just need to change your model a bit rather than start again, then this is going to be good for tracking, and it's not going to be as much work as learning it all in the first place. And in fact, once you've got all these layers of features, basically changing the interactions between high-level features will get you lots of mileage without much work.
So I have another question about the supermarket search. You were saying you just flip a bit in your hash code. So what I'm wondering is, one thing that I'm not sure about is like, if you flip one of these bits, you might not necessarily get something there. I mean, how do you know that you're going to find something there? And then also maybe, is there some way of finding better bits to flip? And like, how do you decide which ones?
So, of course, if you make the number of addresses be about the same as the number of documents, the average density is 1.
Right.
Okay? And if there's nothing there, you flip some more bits.
Sure.
So yes, you'll get some misses, but that's just a sort of constant.
Right.
We can look at actually how evenly spread over addresses it is. And typically, most of the addresses won't be used, and a typical address will be used like 3 or 4 times. So it's not as uniform as we'd like, but that could all be improved. And we've only done this once. We just trained this network once on one data set, and that's all the research we've done so far, really. If we could get a tiny bit of money from someone, we could make this whole thing work much better.
So one thing that is special about digits is that they evolved in a way that makes them discriminative.
Yes.
So you would hope, it's not that surprising that in an unsupervised way, you can extract features that are discriminative. I was wondering what happens with completely other applications where, so clearly when you do unsupervised, you might throw away some very indicative features. Right?
Yeah, so basically there's 2 kinds of learning. There's discriminative learning, where you take your input and your whole aim in life is to predict the label. And then there's generative learning, where you take your input and your whole aim in life is to understand what's going on in this input. You want to build a model that explains why you got these inputs and not other inputs. Now, if you do that generative approach, you need a big computer, and you're going to explain all sorts of stuff that's completely irrelevant to the task you're interested in. So you're going to waste lots of computation. On the other hand, you're not going to need as much training data, because each image is going to contain lots of stuff, and you can start building your features without yet using any information in the labels. So if you've got a very small computer, what you should do is discriminative learning, so you don't waste any effort. If you've got a big computer, do generative learning. You'll waste lots of the cycles, but you'll make better use of the limited amount of label data. That's my claim.
Hi, Jeff. I have a question. What happened to regularization? What kind of regularizations is implicit in all of your stages?
OK, so we're using a little bit of weight decay. And the way we set the weight decay was just we fiddled about for a bit to see what worked on a validation set, the usual method. And if you don't use any weight decay, it works. If you use weight decay, it works a bit better. And it's not crucial how much you use. So we are using some weight decay here, but it's not a big deal. And like I say, all of the code is in MATLAB on my webpage. There's a pointer on my webpage. So you can go and look at all those things and all the little fudges we use.
Right, but the Boltzmann machine is fundamentally sort of entropic regularization, and then your little pieces of tuning with weight decay are from the other family, so you're blending the both somehow.
No, the Boltzmann machine, it's true, there's a lot of regularization comes on from the fact that the hidden units are binary stochastic, so they can't transmit much information. That does lots of regularization for you compared with a normal autoencoder. But in addition, we say, don't make the weights too big. And one reason for that is not just regularization, it makes the Markov chain mix faster if you don't make the weights too big.
Thanks.
Hi. So in your example of digits, you actually tell the algorithm that there are 10 classes.
Yes.
So I wonder what is the impact if we do not give this number correctly? So yeah.
OK, so what you can do is you can take this autoencoder that goes down to 30 real numbers and not tell it how many classes there are, just give it the images, get these 30 real numbers. Then you can take those 30 real numbers and apply a dimensionality reduction technique that Sam Roas and I have developed. And the latest version of that, you can lay them out in 2D, and you will get 11 classes. And it did that without ever knowing any labels. You'll get just these 11 clusters, which is close to 10. It often thinks that the continental sevens are a separate cluster.
So you're saying this is what you have tried, and that's what happened? Or? Okay.
I might even have it in this talk somewhere. I might not, though. It's on my, oh, there you go. That's pure unsupervised on the digits. Now, in this case, these are 2s and these are 2s. In 30D, it's got the clusters. When you force it down to 2D, it wants to keep the 2s next to each other, but it also wants these are the spiky 2s and these are the 7s, and it wants those close. And these are the loopy 2s, and these are the 3s, and it wants those close. But it also wants the 3s close to the 8s. And so in 2D, there just isn't enough space to make 10 clusters. But look, it made 11 there. And if I don't cheat and do this in black and white, you can still see there's sort of roughly 11 clusters. So this was pure unsupervised, and it found that structure in the data. So when psychologists tell you, you impose categories on this data, they aren't really there in the world, it's rubbish. I mean, they're really there.
So the magic number 30, is it, if I choose another number, it will be fine also?
If you choose a smaller number, you might not preserve enough information to be able to keep the classes. And if you choose a bigger number, then PCA will do better, so your comparison with PCA won't be as good.
How does the performance of the digit classification vary according to the number of layers you are using?
OK. Obviously, using the number of layers I showed you is one of the best numbers to use. If you use less layers, it works a bit worse. If you use more layers, it works about the same. I've got a very good Dutch student who has the property he doesn't believe a word I say. And we will know he's using like 40 cluster machines, and he's going to get the answer to this. But so far, I'm right, that using less layers isn't as good, and he hasn't got to more layers yet. He's actually made, with the same number of layers, he can make it work better. And we'll see if he makes it work better with more layers.
So just a bit guess-related question. So it's clear how to evaluate this model, say, if you have some labeled data, and you can try to see if you predict similarly. But if you trade generative, this Boltzmann machines with like especially pairwise interactions in the same levels and so on. If I gave you another set, can you say how good generatively it is, and is it easy?
Okay.
How do you evaluate that kind of part of it?
So the problem with these Boltzmann machines is there's a partition function, and what you'd love to do is take your data set, hold out some examples, train your generative model on the training set, and then say what is the log probability of these held out examples.
Exactly.
And that would be the sort of gold standard. And that's very hard to do. You know the log probability up to a constant, but you don't know the constant. So people in my group are now working very hard at a method for interpolating between Boltzmann machines that allows you to use a Boltzmann machine with 0 weights, which is a pretty dumb model, and then gradually change the weights towards the Boltzmann machine that you eventually learned. And you can get the ratio of the partition functions of all these Boltzmann machines. So in the end, you can get the partition function. You can get a pretty good estimate. This is called, it's a version of annealed importance sampling called bridging. And we think we're going to be able to get pretty accurate estimates of the partition function now by running for like, 100 hours. Yeah. You do this after you've learned, just to show how good you are. But the other thing you can do is you can generate from the model, and you can see that the stuff it generates looks good. And you can then take the stuff you generated from the model, and you can apply statistical tests to that, and statistical tests to the real data, and statistical tests to the other guy's data, the other guy's generated data. And if you choose the right statistical tests, you can make the other guy's data look terrible.
Okay, I think we're out of time now. I'd like to thank Jeff again, and we'll